Welcome to part 20 of a sequence of many videos about parametric curves. We've been using these parametric curves for the physics application of modeling motion. My name is Bill Kinney. I'm actually a math professor at Bethel University in St. Paul, Minnesota. In the past few videos, we've been focusing on the concept of a vector as a tool to help us understand motion and parametric curves. And in particular, we focused on what are called position vectors and velocity vectors. But this begs a question, what is a vector? When we use vectors in this context, and many other contexts, we imagine vectors to be arrows. Arrows have three important properties: a certain length, a certain direction, and a certain position, a certain base, location for the base of the vector. It turns out that the length and direction are the most important things for the algebra of the vectors, but the location of the base is important for the physical interpretation of the vector. There's a natural association between position vectors and points. We want to also think about Mathematica's treatment of that. What is that association? Position vectors are always based at the origin, and the tip of the vector, the tip of the arrow, is always at the location of the object as it moves. Because of that, there's an association you can make, a natural thing that you can make between the vector, the arrow, and the point that it's pointing at when its base is at the origin. Mathematica makes that association too, and I'm going to talk about that in this video. The association can also be made in other contexts like velocity vectors, but it's a little bit more complicated. I'm also going to talk about vector norms in this video, which basically gives you the length of a vector, the operation of scaling a vector, and then get back to our main application of velocity vectors. So we'll go down here and look at our animation from the end of the last video. This is of a motion along a straight line at a constant speed. Let's imagine time to be in seconds and distance to be in meters. The black dot is the object as it moves. Notice it does seem to be going at a constant speed, and it is. How far does it go in 1 second of time? If you measure the length of this with the Pythagorean theorem, you get 5 meters. So it's traveling at a speed of 5 meters per second at constant speed. You also see this black arrow based at the origin with its tip at the point. Okay, evidently that must be the position vector of the point because its base is at the origin and it's pointing at the point. Notice that vector is a vector whose length and direction change over time. It is a function of t, and it is, again, the position vector. What about the blue arrow, the blue vector? Notice its length stays constant. It also points in the same direction all the time, but it does move, the base moves with the point. How long is this vector? What is its norm? Well, hopefully you can at least visually see that it seems reasonable that it's the same as the length of the red line segment when the entire motion has gone through its cycle. In fact, it does have the same length, and the length of this blue arrow is 5. Okay? It's called a velocity vector for the object as it moves. It points in the direction of motion and has a length, a norm, equal to the speed of the object. Once again, just to emphasize, with position vectors, there's a natural association between the point and the vector. Notice on the right side of these equalities, these two things look practically the same. They are different. This one has parentheses. This one has these pointy things that look like a less than and greater than sign. We think of the numbers, the quantities in between the that are separated by the commas here as being coordinates when we think of it as a point, and when we think of it as a vector, we call them components. Arrows are different than points. We want to make this distinction, but there's this natural association. This is pointing at the correct point, so to speak, when you put the base at the origin. How does Mathematica treat this distinction between points and vectors, points and arrows? It depends on what command you're using. Let's go back up here. Listplot is a command that treats this thing, c of h of b, as a point. For example, when I plug in b equals 0.5, it gives me the point whose first coordinate is 0.5 and whose second coordinate is 1. And it plots that point. Of course, when I put a b in there and I put it within a manipulate down here, with b being the animation parameter, then it plots a bunch of points over time. It makes an animation. But c of h of 0.5, c of h of b can be thought of as representing a vector, the components of a vector. When we did it this way, we were thinking of it as being a position vector. We based it at the origin, using arrow and graphics, and we put its tip at this point, and then this whole thing represented the arrow. But then when we made the velocity vector, we did something a little different, something a little strange. We put the base of it at the point, and right here we were thinking of this as a point, and then we put the tip of the arrow at this point, so to speak, and yet we added the point somehow, mysteriously. Okay? What is this operation of addition here? Is it really adding points? Well, conceptually speaking, people usually avoid saying we're adding the points and instead say we're adding the vectors. Now, there is a geometric interpretation of vector addition that's very important. I don't want to get into it in this video, but hopefully in a later video I can get into it. For the purposes of this video, let's just note that the addition that's going on here will add these two vectors component by component, meaning the first component of the answer will be 0.5 plus -3, -2.5. And the second component of the answer will be 1 plus 4, 5. And that's what will happen when you enter this. You get the vector whose first component is -2.5 and whose second component is 5. All right? So just think of it component by component. You might want to look up information about vector addition geometrically and see if you can figure out why this is the way you want to add vectors in such a way that you get the blue arrow that you see here. That's the goal. All right? I also want to talk about scaling vectors. To do that, it's going to be helpful to be able to measure the length of the vector. The word norm in math does mean length, essentially, in this context at least. And, for example, I can find the length, the norm, of this vector. -3, 4, you should know the answer, it's 5. So norm in Mathematica will calculate that. I'm going to use this norm now to do a rescaling. What would happen if I divide this vector by its norm, which is 5? I'll just type a 5 in here. This -3, 4 is getting divided by 5. In reality, it's actually getting multiplied by 1/5. When you say you're dividing it by 5, you're really multiplying by 1/5. What's going to happen is the vector is going to become shorter. How much shorter? 5 times shorter. Okay? It's been scaled down by a factor of 5. The original length of 5 has been multiplied by 1/5. The new length is 1. It's no longer a velocity vector, though it is pointing in the direction of motion, but its length is wrong. It's too short to be a velocity vector. Actually, any vector like this, which happens to have a length of 1, this one does have a length of 1 now, is called a unit vector, and that's a special thing in math as well. What I would like to do to finish off this video is I'd like to allow myself to put a velocity vector in the animation, even in the case where the speed is not constant, for example, when the h of t is square root of t. How can I do that? Well, remember this vector up here has unit length, the length of 1. If I multiply this vector, or if I scale it back up, so to speak, or down if the speed is small, by the speed of b, by multiplying it by the speed of b, that is going to rescale it to give it a changing length. And in fact, because this vector has unit length, length 1, the overall length of this whole vector is going to be the speed of b. And that's what we'll see here. So now you see with the square root of t, remember that's a motion that starts out very rapid and then slows down. You can see this velocity vector is very long to begin with, and as you follow the motion, it gets shorter and shorter. It's pretty cool to watch. It does get shorter and shorter. If I go back and make the square root of t a t squared, that's a motion that speeds up. Starts slow, speeds up. If I make it a 4 times t minus 1/2 cubed plus 1/2, hopefully you recall that's a motion that starts fast, slows down, then speeds up again. Starts fast, long velocity vector, slows down, it gets shorter. In fact, it becomes 0 length at one instant in time, then speeds up again. This is a little confusing what Mathematica is doing there. It's making the vector look like it has a negative length. That's just a quirk, okay? It has 0 length at that moment in time. You can't have a negative length. And with that, I'll end this video.